Hi guys, welcome to our channel, the Tutor. This is the fourth and last video from solution chapter. The first video was about concentration terms, second one was about solubility of gas in a liquid, solubility of solid in a liquid, and the third video was about Rolle's law, Dalton's law, ideal solution and the non-ideal solution. If you have not understood those topics properly, go watch that video and come here for better understanding and better clarification. Today in this video we are going to see the last topic from solution chapter, that is colligative properties. First we will start with definition. Properties that depend on the number of solute particles irrespective of their nature relative to the total number of particles present in the solution. Such properties are called colligative properties. Here we slightly modified the definition given in NCERT because they gave the definition in the flow, that is they explained a few things before and they told these properties. So while you're writing in the examination you have to write as we read, that would be better. And coming back to the definition, it says colligative properties are those which depends only on the number of particles and not dependent on their nature. For example, it will give the same result for covalent, ionic, or polar, non-polar, any type of thing, only the number of molecule matters, nothing else. In that, the first one is relative lowering of vapor pressure. The equation for that is given at the last step. Can you see that? It is delta P by P naught 1. That is the relative lowering of vapor pressure. Let's try to understand how did we get this. P1 equals x1 P01. We get this from Rolle's law. P1 is the partial pressure of component 1 and x1 is the mole fraction and P01 is the vapor pressure of that pure solvent, as we know already. And the second step is we have to calculate delta P1, which is P01 minus P1. From the first equation we get that delta P1 equals P01 minus P01 x1. We just substituted the first equation in the second equation and we got the third one, and from that we are trying to understand the fourth one, that is delta P1 equals x2 P01. We got this from the previous step, that is if we take P01 common from that we will get 1 minus x1. If we have only two components in the solution or the solvent, so 1 minus x1 denotes x2, right? That is x1 plus x2 equals 1 according to mole fraction. So we got that step. So finally the relative lowering of vapor pressure delta P1 by P01 equals x2, which is the mole fraction of the solute. The second one is elevation and boiling point. Before getting into the topic we have to know a few basic definitions, that is what is a boiling point. It is the temperature at which its vapor pressure is equal to the atmospheric pressure. Now we will try to understand why this is called elevation and boiling point. Elevation means increasing, right? So let's try to understand. In a solution we have solute and solvent, and solute in this case will be non-volatile, which means it will not evaporate. So solvent at the normal thing, if we don't have any solute particle, the surface will be fully covered with solvent. So it will evaporate without any problem or difficulty. But think, if a non-volatile solute is present, it will also take some part of the surface. So it will not evaporate also, but it will be there at the surface. So this will create a difficulty for the solvent to evaporate. Thus the vapor pressure of the solvent will decrease. So according to the definition of the boiling point, there should be some more temperature or heat given to the solvent for it to attain the atmospheric pressure. So there is an elevation in the boiling point. Now we are going to see elevation in boiling point's equation. It is denoted as delta Tb, which is equal to Tb minus T0b, where Tb is the boiling point of the solution which has both solute and solvent, whereas T0b is the boiling point of pure solvent in which no solute is present. And delta Tb, that is elevation in boiling point, is equal to Kb into m, where m is the molality, that concentration term, and Kb is the proportionality constant, which depends on the solution taken. From this topic, most probably the question will be like calculate delta Tb, in which they will give Kb also. The only tricky part is to calculate the molality, which we taught in the first video, the concentration term. If you're thorough on this, then this will be very clear and scoring part for you. Our next topic is depression and freezing point. Before going into the topic, we have to know what is a freezing point. It is the temperature at which the vapor pressure of the substance in its liquid phase is equal to the vapor pressure in the solid phase. So adding non-volatile solute particles will decrease, that is depress the freezing point, because the solute particles moves here and there, making it difficult for the solvent to freeze properly. So there is decrease in freezing point, which is called depression in freezing point. Now let's see the equation of depression in freezing point. It is very similar to the elevation in boiling point. Delta Tf equals T naught F minus Tf, where T naught F is the freezing point of pure solvent and Tf is the freezing point of solution which has solute in it. And delta Tf, this is the equation. Delta Tf equals Kf into m, which is molality, again the same concentration term which we used in the elevation and boiling point. Next topic is osmotic pressure. Before going into the topic, we have to know what is osmosis. You would have learned it in the previous class. We'll just try to recall it again. The definition is movement of solvent across a semi-permeable membrane from high to low concentration. Now let's see what is osmotic pressure. The pressure that just stops the flow of solvent is called osmotic pressure. Before we have seen, right, if the concentration varies, then solvent flows from the lower concentration to higher concentration. Now we have to apply some pressure to avoid it, right? That pressure is called osmotic pressure. Now let's see osmotic pressure's equation. Let's try to derive it. PV equals nRT. This is from ideal gas equation, which gives us P equals N by V into RT, where N by V is C, which is molarity, that concentration term, and we get P equals CRT. Now I replaced P with pi because osmotic pressure here we represent it by pi. So pi equals CRT. This is the equation for osmotic pressure. If we have two solutions which has different concentration, that is one has higher concentration and the other one has lower concentration. In this case, if you want to define one with respect to the other, we have two definition, that is hypertonic solution and the other one is hypotonic solution. Hypertonic solution is used when the solution has higher concentration and hypotonic solution is used when it has lower concentration. Now we are going to see reverse osmosis. If we are applying pressure greater than the osmotic pressure, then the solvent will automatically move in the other way. That is, it will not follow osmosis, right? The water will flow from the higher concentration to lower concentration. This phenomenon is called reverse osmosis. It is exactly opposite to the osmosis. And it has many industrial applications like RO water purification. In that, RO means reverse osmosis, and it is also used in converting salt water into fresh water, which is used by many countries. And the last topic in this chapter is Van 't Hoff factor, which is equal to observed colligative property by theoretical colligative property, and it is denoted by I. Let's try to understand this topic with an example. That is, if you are adding 1 mole of KCl into a solution, we are expecting 1 mole of solute in the calculations, but actually KCl will dissolve and give K plus and Cl minus. So it gives 2 moles of solute. Here Van 't Hoff factor plays a greater role. So after knowing Van 't Hoff factor, every formula has a multiple of I in it, as you can see. This is the final formula for everything. Thank you for watching this video, and don't forget to share this video to your friend who didn't understand this topic properly. Bye.